singing in the rain, just singing in the rain. What a glorious feeling, I'm happy. We finally get to do integrals, Physics C people. I am so happy that I am singing in the rain. On to integrals. Integrals start by looking at our derivatives. And so I want to do a quick review of how to do the derivative. If this was our function right here, oops, my pen's not working. If this was our function right here, we know we can take the derivative. We just multiply the 2 times the 3 here and get 6. We lower our exponent by 1. Here we get 6 again, lower the exponent by 1. Here we get 1, and remember this constant goes to 0. We can do that with our displacement to get our velocity. We can do it with our velocity to get our acceleration. And it turns out that to do an integral, essentially we're going to be doing the opposite. We're going to be taking this and going back up to that, or taking this and going back up to that. Since we've done a lot of derivatives, we have a better understanding of how to do what's called the antiderivative, which leads to our integral. So if we were given the velocity equation right here, and they were asked to find the position of the car at t equals 3 seconds, we could do essentially the opposite of what we did to get to the velocity from the displacement. We'd increase our exponent by 1. This t becomes a t squared. And then we'd have to divide, we have to put a number here such that when we multiply the two of them, we get the 4 when we're taking the derivative. So essentially you divide by whatever exponent you put there, so 4 divided by 2. Same thing can happen with this t squared. We know we're going to get to t cubed, but we want to have a 1 when we get there, so we have to put a 1/3 there so it goes away. Constant's really easy. That's going to give us just times a t, so that when we take 2 times 1, we get 2. Now our problem at the end is that anything could be over here. And so when they do a problem like this, they have to tell us what its initial position is, and then we plug 3 in for all these times and get what our position would be. Antiderivative, like an integral, pretty easy. So we can check our work. When we get this for the position, we can take the derivative of it. 2 times 2 is 4t, lower the exponent by 1. 1/3 times 3 gives us 1, t squared, and we get the 2. And so that's the v that we started with. So if we can go one way and the other way, we can figure out what essentially is going to become our integral with the antiderivative. And this is our general form. If we have x to the n and we want to take the antiderivative of it, we take our exponent and go up by 1 instead of down by 1, and then we divide by whatever that exponent is that we put up there. Antiderivative. Not hard. You're almost integrals. We love them. This little slide here is taking our antiderivative and starting with a constant acceleration and taking the antiderivative of that constant acceleration to get our velocity equation. Notice this is v2 equals v1 plus at. We know what that is. And then we can take the antiderivative again. When we do that, our t goes up to t squared. We have to make half of it because that's how you do the antiderivative. The v sub naught goes to v sub t, and then we get x sub naught. Thus, this is our displacement formula. Notice that strange x sub 0 that we had in the AP's formula sheet, and we never understood why they put it there. It's because they were taking the integral to get it. And it makes a lot of sense if you're taking the integral to end up with a constant on each one of these equations as you go backwards. So essentially, this is just using the antiderivative to prove kinematics. So then what do we use integrals for, aside from proving kinematics? It turns out that what integrals are useful for is finding the area under the curve. Last year we found a bunch of areas under curves for things that were nice boxes. And that's easy if it's a nice straight line or if it ends up being a triangle. So just to review that, remember if we have a nice easy equation where work equals force times distance, and we have a force distance graph, we can find out what the work is by finding the area of that curve. In this case, 3 times 6, 18 joules. And we'd like to be able to do that for non-straight curves. That's what our integral will be for. The same way with the derivative, we took various slopes and made x minus x sub 0 smaller, 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 smaller until it was a slope. We're going to find areas by making little rectangles, like this one, and then saying, okay, that's a pretty good approximation of that. No, it's a terrible approximation. But if we make smaller rectangles, we can make a better approximation by adding all these rectangles up. And then we have a delta x that is up on the top times whatever our function is at that individual point. So my work is function times whatever delta x is, because it's a nice rectangle. And what I do is I find that tiny bit of work, I add them all up, and I'll be able to find what the area is under that curve. And so I'm the same way I made my x plus delta x on this smaller and smaller and smaller, I'm going to make my delta x here smaller and smaller and smaller to get a nice sum, since we love those so much. The work becomes the force of x times a small delta x. We can get our approximation for that work. And since we know a little bit about limits, we've done some limits earlier when we were doing our derivatives, we're going to take now our limit as x, delta x goes to 0. We then want to take our sum sign and make it a sum of everything. And then we want our dx, our delta x, to become a dx, which means an infinitesimally small area of x times the whole function. This becomes our integral sign. Integral is a big S, kind of elongated. It's supposed to be summa, for the Latin for sum. And we have some other vocab terms. When we're doing an integral, that's our integral sign. This is our integrand, the thing that we're actually integrating. Our differential is the variable with which we are going to integrate it. The limits are where we're going to integrate it, from the bottom to the top. And we read it as the integral of f of x dx, f as a function of x dx. And these two things, x and dx, have to match or we can't make an integral with them. If we have some constants, that's okay. But if we have anything that's varying that's not x in there, this has to change to something else. So what do we do with this integral sign? Essentially, it's the opposite of a derivative. And so if we have an integral and then a derivative of the same thing, they cancel each other out, which we like to do in math. If we don't have just those two, then we have to do the antiderivative of whatever function is there. In other words, raise the power by 1 and divide by the fraction of that same power. And so if we get something that says, this is dy dx, what is y, that's when I take the integral. And what I do is I separate my two d's. I move that d to the other side, so I have x squared dx, and I'll leave this dy there. Now when I take the integral of a dy, these two will cancel and I just get y. That's nice. This side's a little harder. When I take the integral of x squared dx, I just have to make my power go up by 1 1/3, and on this side I get a constant because it could have anything that would just go away when I took the derivative of both sides. That is really how you take an integral. It is really just an antiderivative on both sides, one side of which is really easy because it's just going to be the integral of a derivative. That's it. Magic. Just like the antiderivative, like to check our work up here, take the derivative of that y that we got, and we end up with exactly what we started with. That's great. And so then we make a nice rule, these nice box rules. This is how we take the derivative of a power function. It's called an indefinite integral because when we do this, we have a constant over there. We're not getting a number, we're getting another function. And so if they ever ask for indefinite, we know that we want things in terms of a variable. We're going to talk about a definite interval after extreme snack time. I'm a little frightened of this one. I'm not going to lie to you. Today, I'm going to have a chip that is seasoned with ghost chili peppers. And I tried this because I didn't want to do it on screen for the first time and die. I did this and I realized that old thing where they say that the reason why we like hot peppers is because they give you adrenaline, that is totally true. These chips are so hot I could feel adrenaline going through my body. It's not pleasant. It makes you kind of crazy. I didn't really like it. And my son tried it too. He likes hot things. And he went a little wacko. Like he started going, He gave me one while I was driving. I almost crashed the car. I really thought I was not going to do it. He picked the one that had the most powder on it and gave it to me while I was driving. It was awful. One of these is not so bad. When you eat 2 or 3 in a row, it's crazy awful. All right, I'm gonna pick one with a lot of powder on it. All right, that one's small but deadly. See that? All that ghost chili on there. Here I go. Oh, okay. All right, I go. I'll be back in a second. Oh my goodness, hot things give me the hiccups, so I think I'm gonna have some hiccups for the rest of this, and I may lose my false eyelashes as I'm crying through this. I'm gonna try to eat 1 or 2 more as I do this, but I don't know if I'm gonna make it. But anyway, let's talk about some more magic integrals. Okay. After we do an indefinite integral, we like to try to find the integral for 2 points, because if we want to find the area, we want to find it between 2 different... Oh, my pen died. Oh my goodness, my pen's feeling the heat too. 2 different points, like we did to find a square. But if we have a curvy function, we're going to want to find it between a and b. That's what we put on the top and the bottom of our integral sign. And we're going to find the integral using our power function that we've just figured out, and we're going to plug these 2 values in for the x to get our answer. The fundamental theorem of calculus deserves another chip. I don't know if I'll make it. Oh my gosh. Okay, hold on. Oh man. Alright. I'm gonna survive this. Alright, here we go. Alright, fundamental theorem calculus says I can take the antiderivative of this to find capital F. When I plug a and b in for my x's and subtract them, that will give me the value of a area underneath a curve, like the picture that I had before. Like for instance, if I had a velocity function with respect to time, and I wanted to find its displacement from 1 second to 2 seconds, I integrate the velocity to get the x's, I plug in 2, I plug in 1, I subtract them, that'll tell me the entire displacement from 1 to 2 seconds. Sorry, maybe I shouldn't have any more of those. I'm not really explaining well. Holy cow. You're not going to believe this when you try it. You should try it, though, because it's an experience. Oh. Ha ha. All right. We'll get some practice of this in class. Not really hard. Integrals aren't hard, at least to start with. If you have these 2 things, find the integral, plug your values in. Okay. Let's talk on an example. Let's say we have a mass on a frictionless surface with a spring. We know we can get, it's a Hookean spring, and last year we only had Hooke's law springs. This year we're going to get some other ones after we learn how to do an easy one. But Hooke's law springs means that F equals kx. We could say negative kx, that's just the direction. But if we did that, we have a nice easy graph to integrate in that it goes up with a constant slope. So we're going to say our constant is 5, F equals 5x, and we want to do the integral of f dx between 0 and 4 seconds. So we want to know how much it is all the way to 4 seconds. We want to know that area. Now this one we could use last year's methods. Look how my lips hurt. But we're going to use calculus, and then we're going to get some harder ones later that we have to use calculus for. And so 5x goes in because that's what my f of x is, and then I'm going to use my general power equation, take my 5 out because it's a constant, and then I do x squared 1/2. I do evaluate it from 0 to 4, and that's how I do it. I do a little bracket, and I put a 4 on the top and a 0 on the bottom. When I put 4 into x squared 1/2 x squared, 4 squared is 16, half of that is 8. I get a constant. And then I'm going to subtract the 0 one. I put 0 in there, I get 0. It's 0 plus c. Notice that when I do a definite integral, c minus c gives me 0. So essentially I have 8 here, 5 times 8, or 40 joules. Quick example. We'll get some more in class, a little more complicated, once the B'ers can help the A'ers. So now, every time we had a derivative equation, like velocity equals a derivative of displacement versus time, we now have an integral also. So if we want to find displacement, we integrate velocity. If we want to find velocity, we integrate acceleration. So this is my velocity function. I can integrate that to get this, I'd have to find out what that c is, or they'd have to tell me what the initial position is. We can do antiderivatives for sine and cosine functions also. Because we know that the derivative of sine is cosine, the integral of cosine gives us back sine. Because I was the anti of them going backwards, right? Because cosine derivative is negative sine, when I take the integral of sine, I get negative cosine. And again, I get c for both of those. I can also do things a tiny bit more complicated. I can take Newton's second law, the version of it that we've been doing for a long time, and I can rewrite A as dv dt, right? And then I can take those two differentials and put them on opposite sides. And so if I do that, I can get ft equals mdv. When I do that, I can then integrate both sides. I can integrate these even though there's no time there, because force would have to be a constant. That's the only way it works. If force is a constant, I can take it out. Mass is always a constant, so I take it out. I integrate both of these, and what I end up with here is force times time. And since this is the change in velocity, I get mv final minus mv initial. That's change in momentum. I get a proof of my impulse formula. Remember, J, it equaled F times T and the change in momentum. So we can take equations that we know and use them to prove other equations. So this equation came from Newton's second law. Crazy. I love math. Magic. We can now integrate. I'm going to send you out some of the immortal Beethoven. I love him. I love integrals. I love math. I love Beethoven. He's amazing. You should listen to more Beethoven. I am positive that you should. Here's a little more. We'll go over some more of this in class. You'll like it as much as I do.